Hello everyone, I'm Felix. Today I'm going to present our work E3, a hardware software co-designed Neuroevolution platform for autonomous learning in edge devices. Edge AI is a driving next wave of AI. As you can see, there are many reported applications. One of them, we call them edge autonomous AI. Some examples like self-driving car, self-flying drone, and self-servicing robot. And the current landscape of deploying this kind of AI is to train the model on the cloud and deploy at the edge and to influence and interact with the environment. However, the challenge of it is that we still want to tune the model to make it better and better. So the current landscape will collect data at the edge and transmit it back to the cloud to retrain and deploy it back. So the problem is there are limited uplink and downlink bandwidth to the cloud. And this kind of scenario need constant connectivity to the cloud. An alternative way is to do edge learning. So we still collect data, however, we just continuous training at the edge. Or to go to extreme, we can just train the data and continuous training at the edge. For both two scenarios, we call them edge continuous learning. However, there are some challenges to learn at the edge side. Edge has limited resources, so we have limited compute resources and limited buffer sizes. And here we consider the application of DNN at edge. So DNN is made of two parts, DNN forward path and DNN backward path. For the forward path, it is usually lighter than the backward path. It can execute with lower bit width. For the backward path, it typically needs higher precision, and at least it has 2 times more number of max than the forward path. For the buffer sizes, at the forward path, we actually don't need to store the intermediate activation. But for the backward path, we need to have a large buffer to store the intermediate activation. So backward path has larger complexity for compute and buffer. Next, we discuss some candidate methods for edge continuous learning. First, reinforcement learning. Reinforcement learning will have an agent and an environment. The agent will make action in the environment and gather the reward and observe the environment and make next action. And the iteration will go on until the environment terminates. And the agent will update itself. Another one is neuroevolution. Neuroevolution is an ES or GA based algorithm. So now let's look at how general ES or GA work. ES or GA will have two parts, evolution and evaluation. And there are some dedicated functions in them. At the start, we'll initialize a population. In the one population, there are a lot of individuals, and in each individual, the basic unit is gene. So after initialization, you will have a population going to the algorithm, and you will evolve them. And then you will evaluate their fitness, and pick the good one as a parent to generate next generation, and so on. Another choice is neuroevolution. So what is neuroevolution? Neuroevolution is a variant of genetic algorithm. The difference is that it uses gene to represent the neural network. And specifically, it represents the weight of neural network. So what I mean is that each individual is a different neural network with the same architecture but different weight. So to run the algorithm, we will initial the neural network architecture like number of nodes and layers. And we will run the algorithm to evaluate the neural network and involve the weight of neural network. The advantage comparing to GA or ES is that it has a wide application because we all know that neural networks are known as good approximation function. Comparing to reinforcement learning, it doesn't have backward path. It only has the evaluate, which is the forward path. However, there are something can be improved. Because we need to predefine the neural network architecture, it means that we can run into the risk of under-provision, which lead to bad performance, or over-provision, which lead to bad runtime or energy performance. And over-provision can be a serious problem for edge accelerator because of limited resources. NEAT is a variant of neuroevolution. The only difference is that it uses gene to represent both weight and architecture of neural network. So as an example here, each individual can represent different neural network with different architecture and weight. So the algorithm is the same. The only difference is that it involves weight and architecture together. The advantage is that The complexity of neural network can adapt to the problem now and avoid under-provision or over-provision cases. Here we summarize some methods for continuous learning, and we consider if they can do continuous learning or not, and their compute and memory complexity, and if their network can adapt to the task. So we start from a typical DNN case, which is supervised DNN, and most of the time it cannot do continuous learning. And another variant is the neural architecture search. So literally, it is searching the neural architecture for different tasks. So the network can adapt to the task, and it can do continuous learning. However, it has very high compute and memory complexity. And we have talked about reinforcement learning, which can do continuous learning. However, it has forward and backward path, so it has comparatively high compute and memory complexity. And you need to predefine the neural network. The basic ES and GA case cannot do continuous learning. And the variant of it, Neuroevolution, has a DNA inside. It can do continuous learning, and it only has forward path, so has relatively low compute and memory complexity. But the network need to predefine. A variant of Neuroevolution need it's featuring the network can adapt to the task, so it can do continuous learning and can potentially not over-provision the network complexity. So to be clear, if we allowed over-provision of unlimited resources, NOS, IL, ES, NEET are all eligible choices for continuous learning. And we found NEET suitable for edge continuous learning use case. Here we propose E3, a hardware-software co-design solution for NEET. NEET composed of two parts, evolve and evaluate. Here we see the runtime breakdown. So evaluate part, the forward path takes 97% of the runtime, as you can see in this graph. To compare with it, we also list the reinforcement learning part. So the forward path of reinforcement learning take from 95% to 45%, so which has a very different characteristic than NEET. Even though NEET has a huge evaluate part, but there are a lot of Parisian opportunity in the forward path. And that's why we design our hardware-software partition. We want to accelerate the evaluate part in the hardware and keep the evolve part in the software. There are some special challenges in NEET accelerator. One of them is irregular network. Because NEET allows the neural network to evolve without any constraint. So it has two characteristics. The network could have sparse connection, as you can see here, and also it has cross-layer connection, as you can see here. It will put some challenge to the typical DNA accelerator. Some DNA accelerator assume dense connection, which cause compute underutilization. Some DNA accelerator will assume layer-by-layer connection, so they could not handle the cross-layer connection, or would introduce large overhead by staging virtual neuron to make it layer by layer. Now let's look at the architecture of E3, Eval Evolve Engine. It has software part and hardware part. Software part is in the CPU, which deal with evolve function, including mutation, crossover, and so on. Hardware part is dealing with evaluate. And we propose a structure for it. It's called INEX, Irregular Neural Network Accelerator, which is very specialized architecture for irregular network. Inside INEX, there are a lot of process unit, PU inside it. And in each PU, there are a bunch of processing element, PE. So what is PE and PU? PE is the basic unit of INEX. It is composed of MAC, activation engine, and local scratchpad. And PU is handling one candidate or one individual or one neural network. So each PU contains a PE array with output stationary data flow, a value buffer, and weight buffer. Now let's discuss about our PU design. So first of all, we look at the typical DNA accelerator, which executes the model layer by layer, and we call it layer-centric execution. So what it does is that it puts the execution of neural network into multiple stages, and each stage is a layer. So like here, we have 3 layer neural network, so that we have 3 stages. And our case is neurocentric execution. It's specialized for irregular network. So to do this, a dependency graph is computed. The weights are ordered and stored in the weight buffer according to the dependency. So you have a neural network like this, and at each stage, you will just put the one that has no dependency, like this 1, 2, 3, 4 node, and then the stage goes on. We also say that we use the output stationary PE array. So there are also other choices for other stationary. So now let's look at what stationary means. Stationary means that the one that we put at the outermost loop of our computation so that we can reuse the most. So some choices could be made like weight, input, and output stationary, and we choose them by two criteria that we use. First is reuse opportunity. The second is the additional overhead or partial sum buffer. Because we focus on NEAT and which use mostly MLP, so they are limited way to reuse opportunity. And in input stationary, it has good reuse opportunity, but it will introduce partial sum. And when the network becomes irregular, the partial sum buffer is large. And in output stationary, it still have good reuse opportunity. And it doesn't introduce any additional partial sum buffer. So that's why we choose output stationary. Now let's look at our Parisian strategy. To be fair, we can pick the number of PU and number of PE as large as possible to maximize our Parisian opportunity. However, your compute utilization rate will be low. So we provide two heuristics to leverage the Parisian opportunity while keeping good compute resource utilization rate. First one is PU heuristic. Because PU is working at the level of population, so we choose the number of PU as factor of population. And the second one is PE heuristic. We choose the number of PE as a factor of number of output nodes. Actually, we try different heuristics for this, like number of total nodes in network, number of input nodes, and so on. And we found this heuristic has the largest chance to keep high compute utilization. Here's our evaluation. We evaluate over 6 OpenAI games with different complexity. And for the algorithm side, we compare with the reinforcement learning, PPO2 and A2C with 2 different configurations. For the system side, the baseline system is the CPU-only execution, which we call it a NEAT CPU. And our case is called E3. So first, we compare with the reinforcement learning. The first 3 graphs is the reinforcement learning with different configuration. And we circle out the one that cannot reach our fitness criteria. So as you can see, the reinforcement learning with small configurations, some of them cannot tackle the task. For the large configuration, it can always tackle the task, and also for NEAT. So either with NEAT can achieve compatible performance with reinforcement learning across all tasks in the evaluation that we investigated. And for all those configuration, we look at their network complexity. So we look at the network number of nodes in the network and number of connection. And you can see that either we NEAT automatically find smaller network with compatible performance. Now let's compare with the baseline system. So we compare with the NEAT CPU version, and we are accelerating the evaluate part. And also, when we are accelerating those parts, we will introduce some control setup and transmission overhead, and all of them are included in the evaluate part. So overall, we have 30 times speed up comparing to the NEAT CPU. Next, we look at our before and after acceleration. So this graph we have already seen before, and after acceleration, the evaluate part only takes 14% of the runtime. So after acceleration, the evaluate part has compatible runtime with other detailed functions inside eval, which are them. So our future work will be to take the next bottleneck part to accelerate it in the hardware. So the candidate could be mutate and speciate. Conclusion. Edge autonomous AI is thriving. However, enabling continuous learning edge AI is challenging due to limited resources at edge. And we identified a variant of evolution strategy called NEAT as one of the promising candidates for edge continuous learning. NEAT cannot be efficiently run in typical DNN accelerator owing to its special problem of irregular network. At this end, we propose a hardware-software co-design solution, E3. Specialized hardware configurations are tailored for NEAT. We propose two heuristics for setting up E3 hardware configuration to leverage Parisian opportunity while keeping good compute utilization rate. Thank you.